So next we'll look at several properties of the conjugate. First, the conjugate of a conjugate is the original complex number. The conjugate of a sum is the sum of conjugates. The conjugate of a difference is the difference of conjugates. The conjugate of a product is the product of conjugates. The product of a complex number with its conjugate is the square of the modulus. And the modulus of a complex number is the same as the modulus of the conjugate of the complex number. All right, so proof. Part 1. Let the number z be the ordered pair xy. Then the conjugate of the number z is the ordered pair x minus y. And so the conjugate of the complex number z is the conjugate of the ordered pair x minus y, which is the ordered pair xy, which is the number z. All right, second part. Let z sub I be the ordered pair x sub I, y sub I. Then the conjugate of the sum, z1 plus z2, is the conjugate of the sum of ordered pairs x1, y1 with x2, y2. This is the conjugate of the ordered pair x1 plus x2, y1 plus y2. The conjugate of this ordered pair is the ordered pair x sub 1 plus x sub 2 minus y sub 1 minus y sub 2. This is the sum of the ordered pairs x1 minus y1 and the ordered pair x2 minus y2. And so the conjugate of the sum is, once again, the ordered pair x sub 1 minus y sub 1 with x sub 2 minus y sub 2. This is the conjugate of x sub 1 with, in the sum with the conjugate of x sub 2. All right? So third part. Again, let z sub I be the ordered pair x sub I, y sub I. Then the conjugate of the difference, z1 minus z2, is the conjugate of the difference of ordered pairs x1, y1 minus x2, y2. This is the conjugate of the ordered pair, which is x1 minus x2, y1 minus y2. The conjugate of this ordered pair is the ordered pair x1 minus x2 minus y1 plus y2. And so this is the difference between the ordered pair x1 minus y1 and the ordered pair x2 minus y2, and this is the difference of the conjugate of z sub 1 and the conjugate of z sub 2. Alright, fourth part. Once again, let z sub I be the ordered pair x sub I, y sub I. Then the conjugate of the product z1, z2 is the conjugate of the product of ordered pairs x1, y1 with x2, y2. This is the conjugate of the ordered pair x1 times x2 minus y1 times y2 as the real part, and imaginary part x1, y2 plus x2, y1. The conjugate of this ordered pair is the ordered pair x1, x2 minus y1, y2 minus x1, y2 minus x2, y1. And this ordered pair is the difference. Correction, this ordered pair is the product of the ordered pairs x1, x1 minus y1 with the ordered pair x2 minus y2. And this is the product of the conjugate of the complex number z1 with the conjugate of the number z2. All right? Okay, so fifth part. Let the complex number z be the ordered pair xy. Then the product of z with its conjugate is the product of ordered pairs xy and x minus y. This is the ordered pair x squared plus y squared, yx minus xy, which is the ordered pair x squared plus y squared, 0. And so this ordered pair has as its imaginary part the number 0, so it is a real number. So this is the real number x squared plus y squared. And this is the square of the modulus of z. All right? So sixth part. Let z be the ordered pair xy. Then the conjugate of z is the ordered pair x minus y. And so the modulus of the conjugate of z is the square root of the sum of squares, x squared plus minus y quantity squared. This is the same as the square root of x squared plus y squared, which is the modulus of z. All right, so that completes the proof. So notice that 1 over z is the same as 1 over z multiplied by the conjugate of z over the conjugate of z, which is the conjugate of z over z times the conjugate of z, which is the conjugate of z over the square of the modulus of z. Further, notice that 1 over z is the inverse of z, since z times 1 over z is equal to 1 over z times z, which is 1. Okay, so we have seen several forms of the inverse of a complex number that we need to be able to recognize as the same number. So for every non-zero complex number, we have that the inverse of the complex number z is the reciprocal 1 over z. This is the same as the conjugate of z over the square of the modulus of z. And if we actually state what the conjugate of z is, we have the form 1 over the square of the modulus of z times the ordered pair, which is the real part of z, and the opposite of the imaginary part of z. All right? So next we can prove a corollary to the theorem. We will show that the conjugate of a quotient is the quotient of conjugates. So proof. The conjugate of the quotient, z sub 1 divided by z sub 2, is the conjugate of the product of z sub 1 and the reciprocal of z sub 2. The conjugate of a product is the product of conjugates, so we have z sub 1, the conjugate of z sub 1 times the conjugate of the reciprocal of z sub 2. Now, the reciprocal of z sub 2 is the same as the conjugate of z sub 2 over the square of the modulus of z sub 2. And so we have the conjugate of z sub 2 over the square of the modulus of z sub 2. This is the same as the conjugate of z sub 2 over the square of the norm, or rather the what we now call the modulus of the conjugate of z sub 2, since the norm or modulus of z sub 2 is the same as the modulus of the conjugate of z sub 2. So in this form, we now see that this is the conjugate of z sub 1 times 1 over the conjugate of z sub 2. And so this is the conjugate of z sub 1 divided by the conjugate of z sub 2. All right? All right, so next we will show that the operation of addition is associative over the complex numbers. So let z sub I be a complex number. Then z sub 1 plus the quantity z2 plus z3 is the same as the quantity z1 plus z2 plus z3. So it will not does not matter how we group the terms, the sum is the same, and so we will be able to omit the parentheses altogether. So proof. Let z sub I be the ordered pair x sub I, y sub I. Then the sum of z sub 1 with the quantity z2 plus z3 is the sum of two ordered pairs x1, y1 plus the ordered pair whose real part is x2 plus x3 and whose imaginary part is y2 plus y3. This is the ordered pair which has the real part x1 plus x2 plus x3 and the imaginary part y1 plus y2 plus y3. This is the same as the sum of the two ordered pairs x1 plus x2, y1 plus y2 with the ordered pair x3, y3. And so this is the sum of the quantity z1 plus z2 with the complex number z3. All right? So next, we will show that the distributive law holds for the complex numbers. So let z sub I be a complex number. Then z sub 1 times the sum or difference of z2 and z3 is the sum or difference of products, z1 times z2 plus or minus z1 times z3. So proof. Let z sub I be the ordered pair x sub I, y sub I. Then the product of z sub 1 with the sum or difference of z sub 2 and z sub 3 is the product of two ordered pairs. The first is x1, y1, and the second is x2 plus or minus x3 with the real as the real part, and y2 plus or minus y3 as the imaginary part. We're going to break this down into real and imaginary parts. So first we're going to look at the real part of the product of z sub 1 with the sum z2 plus z3. This is x sub 1 times the quantity x2 plus x3 minus y sub 1 times the quantity y2 plus y3. So we have x1 times x2 plus x1 times x3 minus y1 times y2 minus y1 times y3. We can choose to group them in the order that we like. We're going to group them in the following pairs. We have x1 times x2 minus y1 times y2 plus x1 times x3 minus y1 times y3. This first grouping is the real part of the product of z1 and z2, and the second grouping is the real part of the product of z1 and z3. So next we'll look at the real part of the product of z1 with the difference z2 minus z3. So the real part of the product of z1 with the difference z2 minus z3 is x sub 1 times the difference x2 minus x3 minus y1 times the difference y2 minus y3. And so this is x1 times x2 minus x1 times x3 minus y1 times y2 plus y1 times y3. And so we have, if we group them in the following way, we have the quantity x1, x2 minus y1 times y2. And from this we're going to subtract the quantity x1 times x3 minus y1 times y3. And so this first quantity is the real part of the product of z1 with the difference. So this first term is the real part of the product of z1 and z2, and the second term is the real part of the product of z1 and z3. And so we have demonstrated that the real part of the product of z1 with the sum or difference of z1 and z3 is the sum or difference of the real part of the product of z1 and z2 with the real part of the product of z1 and z3. So now we need to show that the imaginary parts are the same. The imaginary part of the product of z1 with the sum z2 plus z3 is x1 times the quantity y2 plus y3 plus y1 times the quantity x2 plus x3. So we have x1 y2 plus x1 times y3 plus y1 times x2 plus y1 times x3. Again, we will group them in the following way. We have the quantity x1 y2 plus y1 x2 with in a sum with the quantity x1 y3 plus y1 x3. And so this is the sum of the imaginary part of the product of z1 and z2 with the imaginary part of the product of z1 and z3. So finally, we look at the imaginary part of the product of z1 with the difference, z2 minus z3. And this is x of 1 times the quantity, y2 minus y3, plus y sub 1 times the quantity, x2 minus x3. So we have x1, y2 minus x1 times y3 plus y1 times x2 minus y1 times x3. So again, we will group them in the following way. x1 times y2, the quantity x1 times y2 plus y1 times x2 minus the quantity x1 y3 plus y1 x3. And so this is the difference of the imaginary part of the product z1, z2 with the imaginary part of the product z1 times z3. And so the imaginary part of the product of z1 times z2 plus or minus the sum or difference of z2 and z3 is the sum or difference of the imaginary parts of the products of z1, z2 with the product of z1 and z3. So as the real and imaginary parts are the same, we have that the product of the complex number z1 with the sum or difference of z1 and z3 is the sum or difference of the products z1, z2 plus or minus z1 times z3. And so the distributive law holds for the complex numbers.